one of the best applications of exponential growth and or decay is compound interest. Here is your basic compound interest formula. Banks will use this whenever you put money into an account that earns interest. And so just going through here, I've got everything listed out underneath, but A, that's the amount of money that is in your account. P, I call that the principal. That's the principal amount that you put in. The R is the rate, or the APR, that the bank pays. So annual percentage rate. N is the number of times it gets compounded in a year, and T is measured in years, the number of years you get put in. So I've been having my students just make up a problem numbers to use for the day. Some of them have been nice about it. Some of them have been mean and used horrible numbers. I'm just going to use halfway decent numbers. I'm going to use I'm going to say I'm going to put $2,500 into account. That is going to pay, let's do a 5% interest. Okay. And I'm going to leave this money in here for 10 years. Okay. And I'm going to have it get compounded quarterly. So there's several different ways that you can read this, and that you can see this problem. And I'm just keeping it very general right here. So I want to know what my account balance will be. So this first number, the amount of money that I put in, $2,500, goes in for my principal. And then my R, number one mistake on this, people just put a 5 up here. The bank is not paying you 500%. That would be an incredible bank. If you do find one, make sure you let me know. I want to send my life savings to that account. All right. The N, all right. N in this case is going to be 4. There are 4 quarters in a year, just like 4 quarters in a football game, 4 quarters in a dollar, 4 quarters in a year. So they're going to compound this interest every 3 months, which will be 4 times a year. That same 4 comes up here to the top and multiplies the 10. Now, before I go too far into this, I'm going to show you that this is very similar to the part 1 video. Okay? I'm going to go ahead and do this parenthesis work first. Take 0.05, divide it by 4, and add 1. I get 1.0125. That's just a growth factor. Okay? By the time I do the compoundings and the percent interest and so forth, I'm just taking my $2,500 and I am applying this growth factor 40 times. So order of operations says I got to do that exponent first. So I'm going to take that number to the 40th power and then multiply by 2,500. So my account now is $4,109.05. I like problems forwards and backwards, so I found a good backwards problem. It says a 529 plan is a college savings plan that allows relatives to invest money to pay for a child's future college tuition. The account grows tax-free. Lily wants to set up a 529 account for her new granddaughter and wants the account to grow to $40,000 over 18 years when, I guess, her granddaughter will be ready to go to college. So she can find one that pays 6% interest compounded semi-annually. So to the nearest dollar, how much should Lily invest now? I'm kind of change what I'm asking for on this. I know what I want my account balance to be. I don't know how much I want to put in up front. I have a 6% interest and it's getting compounded semi-annually. It's compounded semi-annually every 6 months. It can be twice in 1 year. And then Lily wants this money to be ready for when she goes to college, so that'd be 18 years later. So, got a little bit of work to do now. When you start messing with people's money, they get a little bit particular with it as far as the rounding goes. If you round the wrong way, I'm pretty sure that your boss is going to get particular with it. So I'm going to try to wait and do all my calculator work at the end of this. So P times this 1.03 to the 36th power. To undo that, I'm going to divide this size by 1.03 to the 36th power. That's that divided by over here. Okay, so that should tell me the amount of money that Lily needs to put in. I'll grab my calculator real quick. 40,000 divided by, oops, wrong divided by both. Divided by 1.03 raised to the 36. And so Lily just has to put in a mere $13,801.30, and that money will grow to $40,000 by the time her granddaughter is ready to go to college. So pretty good deal right there. Maybe you have a grandparent that did that for you. My grandma gave me savings bonds, and I guess that helped out some. I'm going to let you guys work some and make sure you know where to plug everything in. Let me give you a couple. You can choose one of these to work, and I want to kind of talk about these compoundings. So let's do one where it's getting compounded monthly. And then let's do another one where it actually gets compounded daily. And then we'll see what you get. I'm sorry, I'm wanting to use the $2,500 from the beginning of the video with, I'm trying to remember what it was, 5% interest for 10 years. And so plug that in, and let's see what these compoundings are actually doing to my account balance. So even upping the number of times it gets compounded in a year, I did change it some. It looks like I've gone from monthly to daily just with my math up here. It went up $4. So while that's a great thing to have as far as getting compounded more, really in terms of how much money's in there, we're not talking very much difference right here. And we get to the idea of, well, how many times should it get compounded? Could we go monthly? Could we go daily? Could we go hourly? Could we go every minute? Could we go every second? We get to the point where we could just compound this continuously. And that's what this mathematician Euler started working with. And he came up with this number E. Actually, I want to leave this up here. He came up with this number E, okay? And he said that the number E came from just the fact that he put in such a high N right here for the number of times that something was being compounded. And so much so he called it increasing without bounds. So N is kind of going to infinity on that. You can play with this. Just plug in like a million for both of these N's on this equation. And you're going to see that you get really close to this number E right here that Leonard Euler found. It's 2.71828, and it just repeats 1828, 1828, and so forth. And so this number E is used a lot in real world problems. You get on to calculus, this E appears a whole bunch in calculus as well. And so we will be using this for the rest of this unit, this number E. Let's just talk about where to find it. It should be on your calculator. It's either under a log menu, or if you, a lot of you, if you have the Texas Instruments calculator, a lot of times it's on that left side. If it's second in the natural log button. And so the whole idea of the keystrokes on this is that on my calculator, I have to hit second E. I'm not wanting to hit the letter E, but rather the number E. So on mine, I'm hitting second E, and it's going to automatically ask what exponent do I want to put on that E. And so what the exponent I want to put on this one is 1/4. So I hit the 1/4, and I get 1.284. I'll just leave it to 3 decimal places like we did in yesterday's video. Now this number E, we can use it as my growth. used a lot, not my growth factor, but rather just my natural base is what it's called. Okay, so anytime it says that something is growing continuously, if it's a population that's growing continuously, or if it's something that's decaying continuously, what's going to happen is we're going to need to see this number e right here. We're going to come back to that in a later video, but just for today, I want to show you how that e works whenever we're compounding interest continuously. Okay. If I'm compounding interest continuously, my whole interest formula changes to this principal times e raised to the rt, where p is still principal, r is still the rate, t is still the time. And I'm going to be using that e button on my calculator. So let's go back and revisit example 6. I want example 6 to grow continuously. Okay, and so, or get compounded continuously. So I still put my $2,500 up front, and I have e raised to the r, still as a decimal, times t. I don't have all that bulky parentheses to work with this time. So I have 2,500 times e. I'm going to have to put my exponent up, so I know I use the right one. Put in my r and my t. So as you see, it's not going to grow very much at all. $4,121. This time I had 80 cents. What was that from the daily? That's what, 14 cents more than what we had on the daily? So a little bit more money.